If you board a modern commercial passenger jet today, you will fly at exactly the same speed as a passenger flying in the 1970s. For the first half of the 20th century, aviation broke speed records year after year. Then the progress abruptly flatlined. Why did humanity suddenly stop getting faster? To understand the stall, we have to look back at how the physical barrier of speed was originally broken. In 1947, engineers built the Bell X-1. It was a bullet with wings, modeled after a Browning .5 caliber machine gun bullet because that shape was known to be stable at high velocities. Piloted by Chuck Yeager, that experimental aircraft reached Mach 1.06. It was the first time a piloted airplane exceeded the speed of sound in level flight, validating the bullet with wings design for a generation of supersonic fighters. Yeager's flight proved that the sound barrier was a solvable engineering problem. Physics wasn't the ultimate limit to human flight, meaning something else entirely grounded our progress for the next half-century. The first major roadblock was bureaucratic. In 1973, the Federal Aviation Administration issued a strict ban on overland supersonic flight. It was a blunt force reaction to the window-shattering sonic booms produced by early high-speed aircraft. At the same time, the military development cycle ground to a crawl. Legacy defense contractors grew risk-averse, creating a chronic testing bottleneck where it could take up to a decade just to produce a single new prototype. While the United States slowed down, international competitors accelerated. China aggressively advanced its aerospace sector to challenge American dominance. This line graph compares high-speed testing volumes. While the U.S. test frequency remains flat and sporadic, the Chinese curve arcs sharply upward. Since the late 1960s, China has tested hypersonic light at approximately 10 times the rate of the United States. The U.S. lost its aerospace dominance not because of aerodynamic drag, but because innovation was choked by red tape, sluggish 10-year development cycles, and a severe lack of real-world testing. That stagnation is finally breaking. In January 2025, Boom Technologies' XB-1 demonstrator jet hit Mach 1.1, making it the first privately developed jet to break the sound barrier. Private companies can now build these jets cost-effectively thanks to modern engineering breakthroughs. Airframes are being constructed from lightweight woven carbon composites, while the engine sections rely on heat-resistant 3D-printed titanium. These advanced materials allow engineers to iterate quickly on aerodynamic shapes that actively soften shockwaves. Boom achieved its supersonic speed without generating an audible sonic boom that reached the ground below. While the rules of civilian aviation are being rewritten, the commercial sector is only half of the current aerospace revolution. Agile private capital and modern materials are now successfully achieving milestones that used to require dangerous, blank-check government monopolies. The military is adopting this exact startup methodology, directly answering the Pentagon's testing crisis. In March 2026, Hermeus flew its quarter-horse Mark 2.1 drone out of Spaceport America in New Mexico. Instead of spending a decade inventing entirely new propulsion systems from scratch, Hermeus used an engineering shortcut. They powered their reusable drone with the Pratt & Whitney F-100, an existing engine that already flies in the F-15 and F-16 fighter jets. This side-by-side timeline illustrates their rapid iteration model. On the left, legacy defense contractors take up to 10 years to build one prototype. On the right, Hermeus builds an F-16-size drone from start to finish in under a year. This creates hardware richness. By building, flying, and occasionally crashing multiple test vehicles quickly, engineers accumulate real flight data far faster than they could by spending a decade engineering one flawless, risk-averse prototype. Substituting long, hypothetical planning cycles with high-frequency physical flight tests is the only mathematical way the U.S. can close the testing gap with China. The commercial and military technology is ready today, but the laws governing the sky were still stuck in 1973. That changed in June 2025, when a White House executive order specifically addressed this regulatory vulnerability. The order mandated the repeal of the blanket ban on overland supersonic flight. In its place, the FAA was instructed to establish a modern, technology-driven, noise-based certification standard, regulating planes by how loud they actually are, rather than applying a universal speed limit. The stagnant era of risk-averse government monopolies is ending, replaced by deregulated skies fueled by agile, fast-moving startups. The speed of sound has transitioned from an absolute ceiling into a routine flight requirement. 50 years of stagnation ended not with a new law of physics, but with a new set of rules for the sky.